double Wasp engines, final assembly, out in Missouri. These numbers are impossible to think about from my career. Dependable engines. This is what dependable engines means to me. It's not a logo, it's not a nice catchphrase, it's not a corporate banner. In World War II, dependability is saving lives. The 57th Fighter Group, stationed here at Bradley Field, is now overseas. They've got their P-40 Warhawks substituted for P-47 Thunderbolts, and they're now fighting in Italy. The Black Scorpion unit, one of these gentlemen, during a combat mission, goes a little low to the treetops, and this is what happens to the propellers. If my tires in my car have a little bit of imbalance, you know, I'm shaking down there, I can't imagine what this aircraft and this engine had to withstand. It flew 150 miles home. That's what dependable engine means to me. That's what dependable engine means to some of the World War II vets who come to the museum. Not a logo, this. Oh, go the right way, Carl. Here are the numbers. Pratt Whitney, between Connecticut and Massachusetts, these plants, we make just about 129,000 engines. The Missouri plant, 7,900 or so. The auto guys, Buick, Ford, Nash Television, Chevy, 226,000 engines. If you look closely, these are the Pratt Whitney logos. You see the word Chevrolet at the top and Ford. This kind of denotes where they were made. Total war effort, 363,000 engines. 50% of all the horsepower produced in World War II for the Allied forces. Some of the engines of note. Not all, but some. The twin Wasp. It still is the highest produced engine ever in the history of piston engines, 173,000. It will power such planes as the C-47, Dakota, B-24 Liberator, Wildcat, Catalina. The double Wasp, America's fighter plane engine, America's toughest engine. If you come to the museum, we have examples of all of these. The Thunderbolt, the Corsair, the Hellcat, A-26 Invader, all powered by the double Wasp. Not in combat during World War II, but made during World War II, the 4360, the big boy, the largest displacement piston engine that went into mass production. There were others that made bigger, but not very many of them. The Spruce Goose, the H-4 Hercules, 8 of them. The Peacemaker, 6 in the pusher position. And some of the large transport in the first passenger planes. Uh-oh. At the end of World War II, there's this crazy fighter plane from Germany that has no propeller. What? It's the ME-262. It's 100 miles an hour faster than the P-51 Mustang. Oh my God. It's the first operational jet fighter, and this is the first operational jet engine, the Jumo 004. We're behind. World War II ends. I'm going to ask you, is that good news? If you're Pratt Whitney, is that good news? World War II ending is wonderful from so many aspects, except if you're the president of Pratt Whitney, right? In one phone call on some August day, they lose almost 95% of their contracts. They send everybody home. They bring back 6,000 people. So in 1 year, they go from 24,000 to 6. In 1945, they make 50,000 engines. The next year, 2,800. What's the plan? Large commercial engines are still going to need propeller engines for a while. Spare parts sales are going to do its okay for a while. The Navy has asked us to be the licensee, the North American licensee for Rolls-Royce jet engine. We're going to take it. We don't particularly care for the design, but it's going to teach us the tolerances and materials needed to make jet engines. And we're going to ask the Navy, our friend, Navy, for funding to transition from piston to jets. It was rejected. Pratt Whitney's going to have to go it alone. They bet the company, again, on this new technology. These two engines are already in business. So the day Pratt Whitney was allowed to get into jet engines, this is the competition. Frank Whittle in England had developed a centrifugal engine, a turbojet engine. Those plans and some parts were given to General Electric. General Electric produces that engine. It's the first jet engine produced in the United States, and it goes in the first jet fighter. Doesn't make combat. If you remember the P-59 Aerocomet. It's a dog, the Aerocomet. There's some stories about the Aerocomet going up against a P-47 Thunderbolt, and a Thunderbolt just literally flies rings around it. I would say to that P-47 Thunderbolt pilot, wait a while. Those jets are gonna come. Westinghouse was asked to investigate the German design for an axial flow compressor. They do, and they design and build the first US engine that was designed in the US, the J30 axial flow compressor engine. So there's two engines, about less than 2,000 pounds of thrust. Kind of meager. Most of the auxiliary power units on today's airplanes are bigger than that, but it's the start. Okay. Our engine class again. This is Frank Whittle, 1932. This is a basic design of the centrifugal engine. Don't remember too much about it. It's limited to about 5,000 pounds of thrust. It gets to be too big, too quick. It's going to go away. But air comes in the center. The rotating impeller pushes it to the sides, enters in combustion chambers, add fuel, spark, hot gas out the back. Before it goes out the back, it turns the turbines, which turns the front. The Frank Whittle design. But it's important to the Pratt story. Grumman comes up with the F5 Panther. They use the Rolls-Royce Ney engine, centrifugal engine, 5,000 pounds of thrust. It's the best engine around. Navy wants that aircraft. We don't want to have an engine built by a foreign country. Uh-oh, pretty typical today. So Pratt Whitney gets the contract. They get the licensee for the Rolls-Royce Ney engine. We call the J42. So good bar bet. Not that you guys would go bar. But the first engine produced by Pratt Whitney is the J42. It's this guy right up here. We perfect it. We actually go to the next larger one, the Tay engine, the J48. Of course, we put an afterburner on everything. So there's a J48 down the bottom with an afterburner. Gets up to around 8,000 pounds of thrust. The Pratt Whitney Museum has good examples of both of these, especially the J48. I had not seen another J48 with an afterburner. So Pratt Whitney's in the business. This is the other guy's design. This is the Westinghouse. This is the German design. Meet Hans von Oheim. Literature says mostly independent, little asterisk there, mostly independent. He has a different type of compressor. It's an axial flow down the center of the engine. All the blades move at the same speed. The diameter gets smaller, the pressure increases, goes into a burner, hot exhaust gases go up the back. Axial flow. This is the Westinghouse design from von Oheim. This is design used in the first German aircraft. It's the best design. When, in 1950, Pratt Whitney designs its first jet engine, the J57, they use the axial flow compressor design. We make a very important modification. Instead of the whole compressor running at the same speed, we were able to run it at 2 speeds. Instead of a single shaft in the engine, we have 2 shafts in the engine. That change is able to boost up the pressure ratio, better the fuel efficiency, and now we've got, wait for it, a world-class 10,000 pound thrust engine. If you come to the Air Museum and you identify yourself as a Pratt employee, especially a new one, and I'm on board, I will take you to our J57 engine and make you hug it. Because without this engine being successful, Pratt would not have made the transition from piston to jets. I'd still be living at home with mom. It's that important. Collier Trophy. In our business, the Collier Trophy, I think it was 1910 or 1911, is that trophy awarded for excellence in aerodynamics, aerospace, engineering. And the part I like, and you have to demonstrate the technology for a year. The J57 engine wins the Collier Trophy in 1952 for excellence in engineering. That engine goes in the F-100 Super Sabre in 1953. It's the first air-breathing engine Air Force plane that could break the speed of sound. Pratt Whitney has done it again. We have, from the depths of despair, we have now got one of the best jet engines in the world. Same basic diagram you saw with von Oheim, except for the two-stage compressor. Now I have a compressor with two sections, and they run at different speeds. All jet engines today, basically in the core, use this same philosophy today. The dual spool, two shaft engine. It's successful. I don't make you hug it just because I like to make you hug it. It goes into these aircraft without an afterburner. The B-52, the J-2, the U-2 Dragon Lady, the commercial version, Boeing 707. With afterburner, the F-100 Super Sabre. We sell 2,100 or so of them. Speed is an advantage in the 50s and 60s. We like speed. You can outrun, at that time period, most of your threat. Pratt Whitney, on a roll with his jet engine technologies, actually is working on an engine that can go Mach 3 at 80,000 plus feet in altitude. It's a contract by the Navy. The Navy gets disenchanted, they cancel the contract, part prints go to the corner. Then Pratt Whitney gets a call from another part of the government, the CIA. And they say, you know, we heard you've got this engine that might be able to go Mach 3. We're interested. Really? Can't tell you too much, but they're working with Lockheed, and that ends up being our J-58 engine that'll ultimately power the world's fastest aircraft. Now we're up to 34,000 pounds of thrust with afterburner. But the design criteria are, again, considered undoable. At Mach 3.2, the inlet air temperature, the cold stuff, is 800 degrees Fahrenheit. We cannot use anything. The only place in this engine that uses titanium is in the first stage. All the rest, nickel-based and iron-based superalloys. We have to invent new technologies. Those of you familiar with directionally solidified turbine blades, this is the first application we use those in. At those speeds and those altitudes, it's using 60 gallons of fuel a minute at 85,000 feet or above. The gas temperature entering the turbine is 2,000 degrees Fahrenheit. Considered pretty mild by today's standard, but not in 1958. Another nice feature, the afterburner has to be on all the time. I don't mean takeoff, I don't mean fancy maneuvers. 90 minutes on, go down and get some fuel, 90 minutes on. This is a J-58 engine at test. The afterburner glows. Some would say it looks like it's almost like an X-ray, you see through it. No. But very difficult criteria. Pratt & Whitney, I consider it, and all my Pratt & Whitney buddies, it's still one of the most complex engines ever built by Pratt & Whitney. 1958. I'll eventually get it. It goes into this non-airplane. CIA aren't going to really admit it. They built 12 of them, called the A-12 Oxcart. You better recognize it perhaps by the SR-71 Blackbird, but this is the CIA plane that got it off the drawing boards. Recently, last 10 years, there were some records that were declassified, and these are non-records held by the CIA for this engine in this airframe combination. Level flight speed 2,200 miles an hour at 90,000 feet. Single pilot, a little bit short of the SR-71 Blackbird. So we made about a dozen of them, and then we made about 50 SR-71s afterwards. The engine is only about half of the propulsion system. There's a big, long, pointed spike in the front made by the airframer. There's also an adjustable nozzle in the back, also made by the airframer. There seems to be nothing Pratt can't do. So the Air Force comes to us and says, we're interested in a liquid hydrogen engine. Ooh. Pratt Whitney then becomes experts in how to store, pump, transport, and work with liquid hydrogen. We make 5 of these Model 304s in East Hartford, tested in Florida, run on liquid hydrogen.
That's my father. That's my dad.
Good looking guy.
That's my dad.
Model 304. And it really this begins to be so difficult to test, and we don't want to alienate our East Hartford friends, so we're now beginning to buy large swampland in Florida to test this in our rocket business. So this is the beginning of the Florida business. One of the variants of the 304, not exactly, the government has an idea that what about nuclear power? What if we use nuclear power to heat liquid metal that runs a heat exchanger, and we can use that in the engine? The government purchases 1,100 acres in Middletown, Connecticut. Buildings are far spread out because we're doing scary stuff there. And Pratt Whitney will buy that facility when they're done. Again, one of my first trips down to the Middletown plant, as you get off Aircraft Road exit, you go across the stoplight, you travel for 1.25 miles, and there's nothing. Got a house, it's trees, it's like, am I on the right road? And then all of a sudden, you see the main gate, and now I can understand the nuclear engine programs. Well, that liquid hydrogen engine was canceled, but now the Air Force says, can you use what you learned with liquid hydrogen to make a rocket engine? Why not? So we use our technology for liquid hydrogen for a very complicated cycle where we vaporize it to cool the nozzle, we drive a pump that pumps liquid hydrogen into oxygen into the engine, 6,000 degree gas temperature. So many people might not have recognized that Pratt Whitney was one of the first to make rocket engines. Again, we have one of these at the museum. The RL-10 engine becomes the world's first operational rocket engine that uses liquid hydrogen and liquid oxygen. It's the first one that can be restarted in space, and you can change the thrust setting in space. Imagine 289 pounds generating between 15,000 and 25,000 pounds of thrust. Things go wrong, they're gonna go wrong in a bad way very quickly. Still making them. It's this engine. Now, we sold the business several times, Rocketdyne, Aerojet merged with Rocketdyne. It is now, I believe, bill of material for the new Artemis program going to the moon in some of the upper stages. So the RL-10 engine, Pratt, still flying. 1966. Now you're getting close to Keith and I. The U.S. Air Force wants to build a big cargo plane. Got to have 4 engines. We have a design, General Electric has a design, we do not win the contract. We keep working on our design. It will eventually become the JT9D turbofan. I'll explain what that means in a minute. Pan Am wants to build a plane twice as big as the 707. They want to carry more and more passengers, up to 400 passengers, because the seat cost would be less than 30% less than it is today. Look at the size difference between the 707 and the 747. We come up with an agreement, Pan Am and Boeing and Pratt, and we launched the JT9D. If you think about the thrust ranges of the military engines I told you about, the unaugmented, no afterburner thrust of the JT9D is about double the thrust of any engine we've made up to this point. Lots of new technology to make, lots of heartburn and lots of design challenges for the JT9D. Boeing requires us to fly this thing. We haven't had to do that before. So if you went up to the airport, late 60s, you might see sticking out the back end of a hangar the tail of a B-52 bomber, which we leased from the government to put our JT9D on the wing and air test it. Kind of an interesting arrangement. I got about 10 more slides to figure this out. Next to the last engine cover. So if you think about the axial flow turbojet configuration, all the air goes through the engine, 2 different speeds for the compressor, but now I want to do something new. That first fan blade, that first blade, I want to make it huge. I want to make it bigger. I want that front fan to push most of the air, developing most of the thrust rearward. The turbofan configuration. The JT9 we just saw had the ratio of the air going around the engine, colder, slower, more volume, to the ratio of the hot, faster gas going in the center. It's called bypass ratio. The JT9D has a 5-to-1 bypass ratio. So for every 1 pound of air that goes through the center of the engine, 5 pounds of air go through around the engine. The JT9D becomes the first turbofan engine to power a large wide-body aircraft, our 747 frame. Pan Am initiates the service over to Europe in 1970, and now the average person, us, we can afford to go to Europe relatively inexpensively in this new large behemoth 747. What I'd like you to think about for 747 and for jet engines in general, a 747 weighing 360 tons with 400 passengers in a pressurized compartment is airborne in less than 45 seconds. It's phenomenal. We take it for granted. What do we worry about when we're on plane trips? The guy's using my armrest. I didn't get some crackers. It's a phenomenal technology that at least everybody that I've worked with at Pratt, I don't want you to think about. I don't want you to think about anything going wrong with the engines. Military. We are making tremendous strides in military engines. The last couple slides in the military. 1970, a young Carl. The F-100 is our newest military offering. It's going to power the F-15 and the F-16 aircraft. The F-100 will have enough thrust that 2 of them in an F-15 aircraft, the thrust will exceed for the first time the weight of the aircraft, and it allows it to vertically accelerate straight up. I was with the company about a year and a half, whatever. I was dragged into a conference room and they had a little video to show. The Air Force stripped down an F-15, they called it the Streak Eagle, bolted it to the runway, a little arrow, full afterburner. They removed 4,000 pounds of weight. They were trying to beat the Russians to the time to altitude record. Full afterburner, chain is explosively broken. It's airborne within 4 seconds, 500 feet. It reaches the altitude of 18 miles in just over 200 seconds. Oh my God. I'm hooked at Pratt Whitney. I'm going to stay. Just spectacular. The next iteration, using a lot of that technology and made parts of it in my mod center, was the F-119 engine for the F-22 Raptor. Now it has 35,000 pounds of thrust with an afterburner. And just for fun, the military wants a nozzle on the back that can go up and down 20 degrees. I will tell you that pressure vessels like to be round. They don't like corners. Going from the round end to the back of the nozzle, not easy. For the first time, at least in our mod center, we had to use sheet metal and riveting. It was quite a challenge. The other thing that was new for this engine, for manufacturing, stealth. The aircraft that this engine is going to go into is a stealth aircraft, and what we learned is even though the engine is inside the airplane, there's a radar signature from the engine. So for the first time at Pratt, we have to do some modifications, some treatments to the front and the back of the engine for stealth. Very challenging. Our latest engine, using that technology from the F-119, the F-135 is considered the most powerful fighter jet engine in the world. Now it's 43,000 pounds of thrust with an afterburner. One of the variants that goes in the F-35 is a short takeoff and landing. So we working with Rolls-Royce, we run a shaft off the front of the engine with a lift fan, and we can tilt the nozzle down at the back. It's the first aircraft that can take off vertically, transition to horizontal flight, break the speed of sound, come back, land vertically. Phenomenal, and that's what we're flying today. Yeah, I want to not do this.
Yeah.
Final thing on what we're working on today, commercial. My crystal ball says that the large engine competitors will all use this technology within 10 years. I hope I live to see whether that's true or not. This is the geared turbofan. Very clever design. Go back to the turbofan engine that now you're skilled students on. The front large fan is connected to the low compressor. We force the low compressor to run at the same speed as a big fan, and the big fan can't run that fast, maybe 3,500 RPM. What we'd like to do is have the front fan run at its perfect speed and have the compressor run at its best speed. So in 1993, we come up with a couple of ideas, and we have a gearbox, a gear system that's right between the front fan and the low compressor, a reduction gearbox. Now, I can run the fan at one speed. It's a 3-to-1 reduction. So I can run the low pressure compressor around 10,000 RPM. I like that, while keeping the front fan at around 3,000, 3,500. The geared turbofan, 12-to-1 bypass ratio. Keith and I have been on programs for $50 million where we only had 1% fuel burn improvement. 16%, I would have sold my mother and the family tree anyway for 16%. Fewer stages, this is Pratt's engine today. It's having some growing pains, but we're going to solve those things, and this is the future. Pratt Whitney has concentrated on all the single aisles, so if you go on the newest A220s by Bombardier, I think Breeze is flying these.
Breeze is flying.
Yeah, the Airbus product and Embraer, they're flying geared turbofans.
Comment.
Yeah.
In 2012, I'm a member of the American Society of Mechanical Engineers. We had a briefing out at the training center. It was given by the person in charge of the geared turbofan engine program. And he said the hardest problem to solve, I think, was the cooling of the gearbox. That was really difficult. And they had worked on that for a long, long time before they figured that out. And once you figure that out, then it makes it possible. Plus you have other technologies. You've got if I remember correctly, Kevlar around the outside of the fan in case something lets loose. The Kevlar may keep it from getting beyond the engine housing. And there were other technologies, but it was solving the cooling problem that was the key.
Well, let me comment on that. In Middletown, because of the newness of the fan drive gear system,